you have already seen in this textbook. And if you're familiar with my other courses and my other books, and you will know that one of my favorite exercises to give learners is basically to ask you to write functions on your own, functions that already exist. So you've already seen it here with computing the correlation coefficient and cosine similarity. There are two reasons why I often have exercises like this. One is that I think they have huge educational value. You really learn a lot by implementing these functions yourself, even if you end up not using them. And two, it's useful. It's not always optimal to rely on built-in library functions that someone else wrote. Sometimes that is useful, but not all the time. So it's nice to have the skill of being able to write your own functions to implement analyses. Okay, now what I would like you to do in this exercise is basically code or compare the computation time of your correlation coefficient function with the NumPy core coef function. And the goal will be to see basically who is faster. Is your code faster, or is NumPy's correlation coefficient faster? Now, I should say that computation time and speed is not the only important metric in usable code. It doesn't matter if your code is lightning fast if it's problematic. So what you see very often is that code that's comes packaged with professional libraries like NumPy or SciPy, they're not necessarily fast. They can be slower than the code you could write yourself. But, with that increase in computation time comes additional input checks and fixing potential numerical issues and dealing with other kinds of housekeeping things and so on. So there's more to good coding than just computation time. So I don't want you to think that you should never use NumPy's core coef function just because it might be slower than your function. But I also think this is just a fun way to continue exploring applications of linear algebra. So here in the code, I create a new function to compute a Pearson correlation coefficient. This is all the same code that I used earlier in the previous function. It's just a new function because I don't want to waste computation time on cosine similarity when we're not using that here. Okay, so then I import the time library to clock the computation time. And, one of the ideas or the ways that you test computation time is by running a function many, many times. And the reason why you want to do that is partly because there's just some stochasticity. Sometimes computations will take a little bit longer or a little bit shorter, depending on what your computer, or in this case, the Colab server, is doing at the time. And also because some of these computations are so fast that we have to run them many, many times to even get into the tens of milliseconds range. Okay, so what I do here is say to run through 1,000 times. So I'm going to compute 1,000 correlation coefficients between two pairs of vectors, each of which is 500 numbers long. And, these are arbitrary numbers. You can change these. You can have more iterations. You can have longer variables and so on. Okay, so then I initialize the timer. So this is the start time. And then we run through this for loop. And then, I'm just creating variables and computing the correlation coefficient and then seeing how long that took. So what was the total time lag between this call to time.time and this call to time.time? And then I repeat exactly the same thing, but now using the Pearson R correlation. And actually in the textbook, I wrote you should use NumPy's core coef function, but here I'm using Pearson R. I don't have a good explanation for that. Okay, but nonetheless, that doesn't change the point of this exercise. So now let's run both. You can see here I'm printing out the results. So my function took 78 milliseconds and Pearson R took almost a second. So that's a huge difference in computation time. Again, this is because of, let me go back to the previous exercise. Why does Pearson R take so much longer? And the reason is that there's a lot of additional lines of code that the Pearson R function is implementing. So we have this line, we have this converting to arrays, which is not necessary. in our case. This is also not necessary in our case. Um, let's see. So I know that my results are, or my input vectors are already meeting all the assumptions of the function that I wrote, which is not necessarily the case for this Pearson R function. So again, just because my function is faster doesn't mean that it's better. But this is the sort of thing to keep in mind if you are doing millions of correlation coefficients on really large vectors. If you are confident that the data types, the variable types are all solid and meet the assumptions of your function, then, this is good to know. You can write your own correlation function instead of relying on the Pearson R function.